Section 2.1 is going to deal with function notation. This is something that's not new to you, however it may have been a while since you formally discussed it. So we have a relation that would be a pairing of elements from one set that we might call D to those of another set that we might call R. Usually there is some reason for this pairing. So for example, if I have 4 students in my class, I'm going to let them fall in D, and I'm going to have the desserts of cake, pie, and ice cream in R. I can create the relation that Sally likes cake, John likes pie, Mike likes ice cream, Jess likes pie, but Jess also likes cake. This would be the definition of a relationship where our person or the student in our class and what they enjoy for dessert. This relation works the same for numbers. So a function is a special relation in which one member from set D is paired with one and only one member from set R. So in other words, a member from set D cannot have more than 2 partners in R. The above example does not work, however. If we paired each student with their predominant hair color, the resulting set of ordered pairs would be a function. So because Jess likes both pie and cake, it's not a function. However, so long as they didn't have crazy multi-hair colors going on, it should only align with one hair color. There are many examples of this, such as the area of a circle depends on its radius, the time it takes to cook a turkey depends on the oven temperature. Consider the relationship given by the equation A equals S squared. Since we can assign any value to S, it is referred to as the independent variable. The value of A depends on the value assigned to S, and thus A is termed the dependent variable. We can test to see if an equation is a function by doing the vertical line test. A graph of a function will pass the vertical line test. So if I were to have a coordinate axis, and I were to have some graph on it, such as this, the way that I could check to make sure that this is a function is by completing the vertical line test. So I'm going to draw a collection of vertical lines, and ideally it will only cross in one spot in any one of these vertical lines. Alternatively, I can have another coordinate axis, and maybe I have a shape that looks a little different. So maybe I have a shape that roughly resembles a circle. In this case, if I were to go and draw my vertical lines, I'm going to cross in more than one place for each spot. So I'm going to cross here, and I'm going to cross here, meaning that this does not pass the vertical line test, and therefore it is not a function. The members of set D form the domain of the function, while the members of the set R form the range of the function. Functions are often named by using lowercase letters such as f, g, or h. Consider the squaring function, the function that takes the number x and pairs it with its square y. If we name this function f, we could write y equals f of x equals x squared. We can think of a function as a machine that changes a number from a set D, often an x value, into another number in set R, often a y value. So if I were to drop the number 2 into this machine, the machine is going to square my term, and it's going to spit out a 4. So for example, if f of x equals 6x minus x squared, find f at negative 4. So in my notation, I have replaced x with a negative 4, so I'm going to do the same in my equation. So I'm going to have 6 times negative 4 minus negative 4 squared, and then I'm going to simplify. So 6 times negative 4 is going to give me negative 24, minus negative 4 squared is positive 16, and negative 24 minus 16 is negative 40. When I go to do the second one, it's a little bit more complicated. So instead of just replacing my x with negative 4, I'm going to replace it with the entire 3 plus h. So I'm going to have 6 times 3 plus h minus 3 plus h squared. When I continue to solve, I'm going to have to make sure that I follow my BEDMAS rules. So I will distribute the 6 into this bracket, and I will get 18 plus 6h minus, and I'm going to put a bracket around this entire thing. The trick for squaring a binomial is square the first term, multiply them together, so it'll give me 3h and double it, so plus 6h, and then square the last term. Then what I'm going to do is distribute that negative. So minus 9. Minus 6h minus h squared, and combine like terms. So I'm going to have negative h squared, 6h, and negative 6h are going to cancel each other, and 18 minus 9 is going to be minus 9. In the next example, we have that f at d is equal overall to 55. So that means that our f of x is going to be replaced by this number 55, or sorry, negative 55. So it's going to be negative 55 is equal to 6d minus fd squared. What I'm then going to do is I'm going to move everything over to one side of my equation. So 0 is equal to d squared so d squared minus 6d minus 55 is equal to 0. Then I'm going to need to factor this side, so I'm looking for something that multiplies to negative 55 and adds to negative 6. So that's going to be d minus 11 and d plus 5. I'm actually going to complete d below because it is going to take up a little bit of room. Now, d is a little bit more complicated because we actually have our function twice. We have our function with x plus h plugged in, and then we're going to subtract just our regular function. So I'm going to do some color coding as we do this one. So I'm going to start by plugging x plus h into our original function. So I'm going to have 6 times x plus h minus x plus h squared. Then I'm going to subtract my original function, my regular f of x. So I'm going to have minus 6x minus x squared. Putting putting those square brackets around there to remember to distribute them later. And then I'm going to have an h on the bottom. Once I get to this step, then I'm going to have to do some expanding and combining like terms. So I'm going to get 6x plus 6h minus x squared minus 2xh minus h squared, so that is the squaring of the binomial and the distribution of that negative sign. And then to distribute this last negative sign, I'm going to have minus 6x plus x squared. All of this is still over top of h. So I'm going to combine my like terms. I have an x squared, negative x squared, and a positive x squared, so those are going to cancel. I have 6x and negative 6x, so those will cancel. I have a negative h squared. I have a negative 2xh, and I have a 6h. Now, when I look at this, I can actually factor an h out of everything on the top, so I'm going to go ahead and do that. So we get h times negative h minus 2x plus 6 over h, and then I will cancel top and bottom and be left with negative h minus 2x plus 6. For our last example, we can actually use a graph such as the one given here in order to determine values of a function as well. So here I've been asked to find f at negative 1. So what I'm going to do is I'm going to go over to my graph and I'm going to find negative 1 where my x values are, and I'm going to move up the grid and find that this point here where x is equal to negative 1, my y value is equal to 3.6. So f at negative 1 is 3.6. Similarly, f at 0, I'm going to follow this line at 0 up to where it crosses my graph, which is right here. My y value is 3, so f at 0 is equal to 3. The other thing that we can be asked for is where f of x is equal to 2. So that's really asking us where our y value is equal to 2. So I'm going to go to 2 on my y value, and I'm going to go across this line and say, oh, right here is where it's equal to 2, and if I go down, this position on my x-axis is equal to 1.5. So f of x is equal to 2 when x is equal to 1.5.